All right, good morning, everyone. I really enjoyed yesterday. I got the green light. Okay. You're good. And you can hear me back there, okay? Someone in the back row, thank you. Anyway, I really enjoyed all your engagement yesterday. I appreciate your curiosity for this subject matter, and it was a real pleasure for me. So I look forward to more. It also reminded me of my own time here 31 years ago, and actually I told one of you, I won't say whom, about my first week here when I organized an ultimate frisbee game, and 1 minute into the game I sprained my ankle, and so I couldn't hike the whole time here. And I'm telling you about that because the response I got was, "Wow, ultimate frisbee was played way back then." Yes, it was. But just thinking about my time back here, I remember, also being really excited about particle physics and cosmology, and really grateful I had the opportunity to be here to learn all these things, and excited about where I was in graduate school and the research I was doing, and at the same time, as all that, excited and hopeful, also terribly insecure, and I just want to, and I think that's not just me. That's actually fairly widespread. And I just wanted to, so I also think it takes some courage as well as curiosity to be here and engage with that in the presence of, very human things that come up when you are trying to, your goal is to discover things that nobody else knows yet, right? To figure things out that no one else has done. It's very challenging, and it's because you're going into the unknown. It's a really ripe situation for insecurity to raise its head. So that insecurity hasn't gone away, throughout my whole career. I react even when I've just done something I'm really happy about and I feel like was a contribution. There's always the thought, well, yeah, but I'm probably done. That's probably the end. No creativity is going to come out of me again. I had a good ride, and fortunately I don't pay too much attention to that thought. I turn to my curiosity. What am I curious about? What do I want to do? And that's been a faithful guide. So I just wanted to share that with you as we get going. Your curiosity is also inspiring to me. So today we're going to talk about CMB temperature anisotropies as probes of the dark universe, as a probe of the dark universe. And this is going to be at my goal here is to give you some physical intuition about how measurements of cosmic microwave background anisotropies tell us about the dark universe. But if you're going to do this professionally, then you should know that the way to really do this, and I'm not going to be doing this, is to solve the collisional-Boltzmann equation for these phase-space distribution functions for the different quantities, and coupled with gravity. Right, and this depends on these phase-space distribution functions. In a way, that's all the that's all the equations we have. It can be written down very compactly. Actually working these out, what these are, and solving them can be complicated. And a good resource for this is a book called Modern Cosmology by Scott Dodelson. And also there's a useful paper, a paper that's still useful to this day, by Chung-Pei Ma and Ed Bertschinger in 1995 that I'm sure you can find, that helpfully writes down the Boltzmann equations and Einstein equations, the perturbed Boltzmann equations and Einstein equations in 2 different gauges. So it's another thing we won't talk about here, but this split between what's the background and what are the perturbations is there's some arbitrariness to it, right? You can make slices of constant time through a inhomogeneous universe in different ways, and choose that split. And so there's different ways of defining constant time surfaces. These are called gauge choices, and they actually write down the equations in 2 often used gauges, conformal Newtonian which is often what's used in the theoretical literature, and then in synchronous gauge, which has some advantages for numerical implementation. So it's helpful to see the relationship between the 2. Of course, there's publicly available codes that, typically people don't start from scratch these days. There's great codes available like CAMB and CLASS, and there's a lot of information in the documentation for these things if you want to engage in this, actually calculate something. Okay, so CMB temperature anisotropies as a probe of the dark universe. I want to start off talking about the causal structure of decelerating and accelerating spacetimes. Well, spacetimes is too general. Decelerating, expanding FRW universes. So that's Friedman, Robertson, Walker. That's the spherical. That's the homogeneous and isotropic spacetimes we've been thinking about. And so decelerating first. So let's just think about 2 stationary observers. So in a homogeneous universe, there's a very particular time slicing, which is choose time slices that are at constant density. So that so if we do that, right, we can lay down coordinates they give the invariant distance that I wrote down yesterday, and then if you're at rest in that coordinate system, you see the isotropy and the homogeneity of the CMB, and we call these co-moving observers. So let's take a co-moving observer at some point A and another at some point B, and if the space-time is decelerating and expanding, then, well, because they're expanding, then these are getting, further apart. So this is actually physical distance. I'm between them that I'm plotting. Their co-moving distance is staying the same, right? So this motion is all a result of expansion, and so they're expanding. So this is getting closer, and it's decelerating. So which means in the past that expansion is actually faster. And if we take say this is a radiation-dominated universe. Right, we have h squared equals 8 pi g rho over 3. So this is proportional to t to the 4th. There's a whole bunch of cosmology I'm assuming you've had some exposure to, right? So this temperature is inversely related to the scale factor. So the expansion, as we go back, you can work this out. A finite time in the past, we get to a equals 0. The expansion rate diverges. And if you work it out, this is at this singularity, expansion rate's infinite. A and B even though they're in the same location, are moving apart from each other at an infinite speed. And the structure is that you go from being, let me just guess that the transition is here. This is superluminal. All right, so A and B moving apart from each other at faster than the speed of light, to subluminal. And so we go from being, these points A and B, it doesn't matter how far apart, say you chose these at some given time, no matter how far apart you chose them in the past, at A equals 0, they're going to be right on top of each other and moving apart from each other at an infinite speed. So they all go from superluminal to, if you wait long enough, to subluminal. And so they go from being in causal contact, out of causal contact, to in causal contact. And it's one of the puzzles if we don't add inflation. So any wavelength of perturbation that we evolve, if we just have radiation dominated back to the singularity, then all of these perturbations start out on length scales that are out of where a crest and a trough are out of causal contact. So how did they get created? It doesn't seem like there's be a causal mechanism for it. Okay, that's decelerating space. Oh, one other thing I want to say about it. This split, this transition from superluminal to subluminal, I won't bother deriving it, but the physical size of the wavelength then is up to factors of order unity equal to what we call the Hubble radius, or the horizon, particle horizon, for being more precise. And in fact, to distinguish it from another kind of horizon that I'm going to that'll come up next, this is a past horizon. The past horizon is, if you calculate, well, from the beginning until some current time, how far can a light signal travel? So that's this border, right, between what's in contact and causal contact and what isn't. Okay, and then in accelerating space-time, we have, right, the opposite situation, where we move from subluminal to super. I don't know, let's say it's here. Right. And so from in causal contact to out. And let's see. In the inflationary universe scenario, oh, right. And then also this transition is it, why did I say that? Well, if this is the condition, right, for in causal contact. And again, up to factors of order unity, when A and B are separated by, oh God, if this is larger than this, you're out of causal contact. You guys are a little slow to maybe starting at 9 is not as good as starting at 10:45. Since I've been on the planet so long, as someone pointed out, Waking up this early is no problem for me. Lambda, so this, of course, is still the criterion for being out of causal contact. The difference is that you go from being in causal contact to being out, and then you go from being out to being in. And in the inflationary universe scenario, we patch these together. So we have this, oops, I don't want to change the sign of the slope. So again, A and B, and then we patch in here, some accelerating space-time, right? So this is probably too hard to see. Let me just blow this up, right? And we've got what's going on in here. Is this. So this is this acceleration happening during inflation. And then inflation ends, you reheat, you map onto the hot Big Bang, and so hot Big Bang. So let me plot here as far as thinking about the generation of perturbations and in this causal structure, how it works out. This is a really useful diagram where we plot physical length scale versus scale factor. And in the limit that the energy density is completely constant during inflation, then we have exponential expansion. So if the energy density is constant, H is constant, right? H equals A dot over A by definition. So the scale factor grows exponentially if H is constant, which is what you have if the density is constant, which we can nearly have during inflation as say the energy is dominated by the potential energy of a scalar field, and the scalar field is not changing very rapidly. So in that case, C over H is constant because H is constant, right? That's the size of what we call a future horizon. A and B are beyond their, right, at this point, A and B are beyond their future horizon. They're not, if A sends a light signal to B, it won't get to B ever, right? Even in an infinite amount of time. That is C over H. And then at some point, inflation ends, and there's a reheating process, and then you're in a radiation-dominated universe. And then radiation-dominated, and then at some point, this softens some because you're in matter domination. And then apparently, we're back to lambda domination again, right? And we're in that transition now, amazingly. So this is all this horizon, and now if we take a perturbation length scale, the wavelength of a perturbation, physical wavelength, it's stretching up with the expansion. And I mean, what you might expect from this story of out of causal contact in causal contact, out of causal contact, in causal contact, right? You see this wavelength starting off smaller than this horizon, and then becoming larger than the horizon, and then becoming smaller than the horizon again. And right, when that happens depends on the particular wavelength you're talking about. So this is one co-moving wavelength, and another, say a larger one, right, will be just completely parallel to it. Okay, so that's, so how many people, I mean, I imagine a lot of you have seen this picture before, but I don't know how many. How many people, I mean, have seen, a diagram like this or its co-moving version? Right, okay. So, right, why are we talking about wavelengths of perturbations? It's really convenient to think about a single cosine pattern evolving at a time. Why? Because the equations that govern that motion are decoupled from all the other cosine patterns, right? So that's why we evolve single wavelengths, and also they're simpler. Then the equations are governed by ordinary differential equations rather than partial differential equations. So, does anybody want to, I don't know, this might be too much to ask, but again, I'm uncomfortable when I'm the only one talking for so long. Since a lot of you have seen this picture, does anyone want to explain why, just on the basis of this causal structure, why we would get, well, let's take it in several steps rather than asking for the whole thing. Why would the, at horizon exit here, the perturbation amplitude be equal to the perturbation amplitude at horizon exit here? Yes? Right, right. So the Hubble rate is the same here. The density of the density of the scalar field energy is the same all the way across here. Nothing's changing. So the physical conditions here are exactly the same as the physical conditions here. There's nothing to distinguish these two. And so if I write, and so the amplitude of the perturbations crossing here are equal. Let me give us some language for talking about the amplitude of the perturbations in the way I want. Or let's see. Yeah. So delta rho, one way of, I'd like to talk about delta rho over rho on some wavelength lambda, and let me, that's clearly some dimensionless thing. And I'm gonna give out some exercises for the relationship, for understanding what power spectra are. And but for those who already know, this is k cubed p of k over 2 pi squared for k equals 2 pi over lambda. And so inflation is a nearly time translation invariant state. So we got delta rho over rho at the exit, say at time t1, equals delta rho over rho at the exit at time t2 for the wavelength that's exiting, right? And nothing happen now. So the next thing I want to claim in a very hand-wavy way is that in some sense nothing happens outside the horizon, right? There isn't time to transport. So, yes.
So if these T1 and T2, are they inflation is nearly time translated? Okay, never mind.
Yeah. So this is. Let me mark that. Yeah. So this is time T1, time T2. That's what I mean here, right? Now, nothing happens, to a first approximation, nothing happens outside the horizon. I mean, if everything's outside the horizon, there's no time for any transport to occur, right? How growth of perturbations occurs is you've got transport from underdensities into overdensities. There's no time for that to happen, right? The wavelength is larger than the horizon. You're out of causal contact. And so we also have delta rho over rho exit of T1 equals delta rho over rho entrance at, I don't know, I guess I should call this T3. So if this is 1, oh, maybe I should call it T4, just to get them ordered correctly. Right, so and then I'm calling this T4. So the result is that if we specify the perturbation amplitudes at horizon crossing as they cross the horizon here, then we get that, right? We have the same thing for T2, so this equals what was here. These are equal to each other, so everything's equal, and we have a spectrum that doesn't change. At least if we're talking about it in terms of k cubed p of k, it's not changing. The amplitude's the same at horizon crossing. And now I said that nothing happens outside the horizon, but there is one thing that happens, and I'm just surprised that I didn't get this into my notes, but it's okay. Let's see. Yeah. Yeah.
Outside the horizon for say like a plane wave perturbation, wouldn't there still be just a very small amount of dampening from the small parts of the wave that are in causal contact and are slightly?
Yes. Okay. Yeah. Yeah. So this is, yes. So these are continuous things. I'm talking about horizon crossing like it's some, automatic change to the dynamics. So in general, everything is smoother. That's right. Right. So what does happen, crucially, to how the CMB temperature anisotropies show up, to a particular feature in the CMB temperature anisotropies, is that all the momenta, if there are any momenta in the fluid, say, so right after this is reheating's done, we have this plasma here. Let's think about what's happening in that plasma while for a perturbation wavelength that's much larger than the horizon. There's no time to respond to any forces that are present, gravitational potentials or pressure gradients. But in an expanding universe, we have this, symmetry of spatial homogeneity, and and that leads to a conserved quantity. And it's not hard to work out, but I don't want to take the time to do it, and most of you know it. The result is if you have this homogeneity, then you have PA equals constant, where this is momentum times the scale factor. That's the conserved quantity. It's not the momentum itself. And so any momentum perturbations in the fluid are being damped away to 0 by all the expansion that's happening. This means that when things can finally start oscillating, I seem to have like missed a page in my notes, but this means that when things can finally start oscillating, if you think about a particular wave, we have the initial conditions for one thing, for standing waves. So these Fourier modes in the plasma, so you have this cosine pattern. Say this is a crest here and a trough here. And once the pressure and gravitational forces can start operating, we have a harmonic oscillator equation describing that amplitude. And it's a standing wave. It's just going like this. So these things aren't traveling, and that's because we're starting off with 0 momentum. The other thing is that because they're all starting off in the same phase, and so modes with same wavelength have same oscillation frequency. And so they have this temporal phase coherence. So they're all oscillating together. And the result is well, let me give you just a simple geometric picture of how we actually see this plasma before telling you about the result of that temporal phase coherence. So, seeing the plasma. So what's great is that we get to see this plasma. It's amazing, and we're getting to see this plasma when the physics is so simple, right? That linear perturbation theory is an excellent approximation. We know how to do linear perturbation theory really well. And the plasma has been gravitationally influenced by anything that's sourcing gravitational potentials. So in ways I'll show you, this turns out to be a great probe of the dark universe. So here's, this is our imagining our past light cone here. This is us here and now. This is back when the universe transitioned from being ionized and opaque to being neutral and transparent. Just crossing this boundary. So this is what we call the last scattering surface. And right, we've got photons traveling to us from that epoch. What fraction of the photons we see come from that epoch? Good, yes, right. So tau is about 0.05 or 0.06. If tau is 0.05, we're seeing 95%. We're seeing 95% of them from here, and 5% have scattered off of the reionized IgM instead. So 95% of them are coming from here. We are imaging this thin annulus around us, and if we have, let's think about what a single Fourier mode looks like in projection. Whoops. Well, this is a pretty I mean, I'm trying to draw crests of a Fourier mode, and I wasn't careful enough. Okay, anyway, I give up. You know what I'm trying to draw. And how does a wavelength project into an angle today? Let's call this lambda sub theta, right? So this is lambda. If I don't write physical on this, it's a co-moving wavelength, right? And the physical wavelength is a times that. And so what's the relationship here between, no, I'm calling this theta sub lambda. So theta sub lambda equals lambda over the co-moving angular diameter distance. Basically by definition of co-moving angular diameter distance, but
Could you express that by co-moving? Do you mean like a divided by h or something like that? Or
so
1 over h, or
so by you mean for this here? But, so this. The reason this is the co-moving angular diameter distance is because I put in what I put in here was the co-moving wavelength. Okay, so I could also the only difference between co-moving angular diameter distance and let's just call it this, you know, just the angular diameter distance. Is what's implicit here. So it's a factor of A that relates the two. I can, in case this is helpful, I can also tell you that for k equal, well, even if k isn't equal to 0, in FRW, if we put the origin here and say this is at coordinate value, radial coordinate value R1. Right? And we talk about that as a co-moving coordinate, so that kind of makes sense.
So this is confusing because I've also heard co-moving used to describe a coordinate system where g equals eta locally, like locally flat, and that's the opposite of the FRW.
What's g?
Oh, g being the metric, so that they.
Little g.
I've heard that you describe a coordinate system as co-moving if at some special point of your choice, locally the metric is equal to the Minkowski metric, which is not the true for the FRW metric. So it's in that case you'd think it would be the other way around. That's why it's confusing.
Even for the well. Anyway, maybe we could talk about this afterwards. I'm concerned about getting derailed. There's a groundswell of no, I'm going to go on. Now, I also told you yesterday that we expand. Well, I don't know whether I told you this yesterday or not. But this temperature map, I'm sure you've seen this. This is the analog of our Fourier decomposition, and so these are our analog of the Fourier coefficients. The spherical harmonics the important thing to know about them is that in over 360 degrees, or 2 pi, they do L complete oscillations. So, if you like the wavelength, if you're going to do a wavelength times 2 pi, shoot, how am I translating that into, so 2 pi times, no, that's not what I want. Theta lambda over 2 pi equals 1 over L. Yeah, so another way of writing this, L equals 2 pi over theta lambda. So L behaves just like K. So again, right, the important thing about the spherical harmonics here for these purposes is that they do L oscillations going around the complete circle. And that translates into this relationship between L and wavelength of a given spherical harmonic. This is just like the relationship between K and wavelength, right, for our three-dimensional Fourier modes. And so we can then make this connection that there's this, right, here's the mapping between L and angular wavelength. And we have theta lambda is lambda over dA. So this is 2 pi dA. And theta lambda is lambda over dA. Right, I'm getting what is going on here? Theta lambda is lambda over dA. Right, I've got that one factor of dA, and I got the lambda here. Right, and then lambda is the 2 pi over K, so this ends up as K dA. Equals K dA. So this is the mapping. We have this mapping between K and L. So in real space, right, this theta lambda is lambda over dA, and the Fourier space version of that is L equals K dA. And let's think about now about what's happening at last scattering with modes of different wavelengths. Yeah, I'll write this. So in time, this harmonic oscillator, right? So the speed of sound is not the speed of light. So this isn't cosine of k times conformal time, but cosine of k times the sound horizon. So as the sound horizon goes, the sound horizon is telling us how far a sound wave can travel from the beginning until any given point in time. This is the co-moving sound horizon. And let's look at it in right, it's a cosine because we're starting from rest. So the amplitude of this spatial pattern in time is harmonically evolving like this. Gesundheit, yes. How do we define what? The sound velocity so this adiabatic relationship between pressure and energy density is how we're defining the sound speed here. And this is 1 over 3 times 1 plus r, where r equals, let me get this right, r equals 3 rho baryon over so this, if we just had, if we didn't have the baryons in there, so if r were 0, 3 rho baryon over 4 rho gamma, then the sound speed of this completely relativistic plasma would be square root of 1/3. There are baryons in the plasma. They're adding inertia. They aren't adding much pressure at all. So they're contributing to the energy density, but not the pressure. And that inertia ends up lowering the sound speed. So that's why r is coming in here in the denominator. Anyway, so that's the sound speed of the plasma. Now, if we look at this, if we evaluate this at recombination, right, this epoch when we get to start to see the plasma, we have, let me not write any more on that. I guess I'll go over here. Going like this, and this axis is k, which equals L over dA. So this is a square of that cosine pattern. So we get this series of peaks. It doesn't look at all like the CMB power spectrum you've undoubtedly seen, because there's a lot of effects we haven't included. But that temporal phase coherence has led to this peak structure, right? So there's a whole bunch of modes that hit their first extremum of oscillation just as the plasma disappears. And all those different modes, they have the same starting point. They start at the same phase, right? They're starting from rest, and they're oscillating at the same frequency. This is sound, and they have the same wavelength. They're going to be oscillating at the same frequency. So they all hit an extremum at the same time, and they all project into this angular scale. And then there's modes, right, that undergo. They hit their first extremum and go to their next extremum. Those are smaller wavelength modes, so they're oscillating more rapidly, and they come out here. There's ones that just hit a null, right, and they're those ones. And from looking at this pattern, we can, let's say this is L1 and this is L2. There's an important thing for probing the geometry of the universe that comes out of this. So delta L equals L2 minus L1 equals K2 dA minus K1 dA, and this equals K2 RS at recombination minus K1 RS at recombination times dA over RS at recombination. And what do we know about these values? These are peaks. Well, they're one extremum and then the next, which is half a period away. So they differ by pi, right? So this difference is pi. And this is the angular size of the sound horizon. This is 1 over the angular size of the sound horizon that we see today. So this delta L equals pi over theta s. And so very roughly, it's that spacing between the peaks that allows us to infer the angular size of the sound horizon, which, as we'll see, is going to be very useful for figuring out, well, it's useful for figuring out what this angular diameter distance is. So we'll see how we can calculate this. So we can measure the angular size of the sound horizon, so we can infer this. What this has in it is, right, how far away the last scattering surface is depends on the whole history of the expansion rate, which is informed by what the universe is made out of, right? So this is a probe of the contents of the universe. And then on Friday, we'll get to baryon acoustic oscillations, where we can probe this angle from over different distances, right? So we can use a feature that arises from these acoustic oscillations, a feature in the correlation function of galaxies, to do this, infer these angular diameter distances over a range of redshifts. Okay. Thank you.
Sorry, I don't understand the dimensions on the delta L.
Well,
The line up. It seems like you have a dimensionless and then a dimensionful and then a dimensionless. I'm missing something, but I don't.
okay. So K has units of inverse distance, right? So everything here is dimensionless. I mean, this term is dimensionless. Okay, right? Did that clear it up? Or so?
No, so the second line seems to be.
Did I?
R units of length.
So all I did in going from here to here is I multiplied. I factored out the dA, and I multiplied and divided by RS star. So this is also dimensionless. This is dimensionless. This is dimensionless.
Wait, sorry. What's in the denominator of the dA thing? Is that an RS?
It's an RS star.
Sorry, I thought it was CS. Sorry.
Okay. Anyway, sorry I wasn't clear. Yeah. Thanks for asking.
Isn't that combination just 1 over CS?
No. No, because CS is changing with time. And also this is the so let me anyway, a drawing can be worth a lot. We're talking about, well, I guess I already made the drawing here. So I'm talking about how, so we talked about this as wavelength, but what if we're projecting the sound horizon? So there's the sound horizon. This depends on the history of the sound speed and the expansion rate from the beginning until this decoupling happens.
Doesn't the sound horizon not depend on wavelength? Isn't it just the?
No, it doesn't depend on wavelength. Sorry, I should have drawn a different drawing. Let's say this is the sound horizon, the co-moving size of the sound horizon on the last scattering surface, and right, this is theta s. Right, this is dA. So this distance has nothing to do with sound.
It has to do with light, though.
Yes.
So and light travels at speed 1. So
Yes.
If it travels that distance.
I can tell you that at least in a flat universe, in a flat universe, this works out to be integral dz over h of z. Yeah.
Wait, isn't that isn't dA just 1 over a times h? h? Or there's
So
different ways of defining it. The horizon,
let's just take this one-dimensional metric, right? And we have, so if for ds equals 0, we have c dt equals plus or minus a of t dr. And then, because as you said, this is light we're talking about, so ds is 0. And so we've got c dt over a equals dr. And if we, and actually we've got a photon, coming in from higher r to lower r, so let's choose this branch of the square root. And if we integrate this up, this, and let's, let me put the minus sign over here. This is going to be equal to dA. This is just going to give us, if we're going from 0 to R1, so this is 0 and this is R equals R1, that's R1, which I told you earlier equals dA. And then this works with the change of variables. You can show that this is, at least in a flat universe. Well, yeah, yes. Well, even more generally.
Okay. Yeah, so wouldn't the sound horizon just be that times the speed of sound?
Be what times the speed of sound? None of this has anything to do with the sound horizon.
So if we were looking at what sound is doing, it would do the same thing as light, but slower by a factor of cs?
Oh, the same calculation. Yeah, absolutely. So instead of having c here, we just have cs and we bring it in the integral. Yeah, exactly. Yes. And then we'd be calculating the sound horizon.
Yeah. So this would mean that rs is just d times cs, wouldn't it?
No.
All right, we'll talk after.
Okay. I mean, it's over. This is from, as far as time goes, this is from recombination to today. The sound horizon I'm talking about is from the beginning until recombination. So it's over a different.
Oh, okay.
Okay, now I want to talk about a really important effect that we haven't included in what we did so far. It's really important for constraining anything that's sourcing gravitational potentials while the modes that we measure are entering back into the horizon. And this is kind of a cool effect that Hu and White called radiation driving. And before we get to the radiation driving, I want to, instead of doing any derivation of this, given how time is ticking away, the important thing to know is that in matter domination, the gravitational potential of a given Fourier mode is constant. So we have this Poisson equation and delta rho, well, let me just write this. So this we can think of as minus k squared over a squared. I mean, this is a physical Laplacian, so it's the we get this factor of a since we're using co-moving wavelength here. And we can write this. And so phi equals constant is consistent with, so this is going like a to the minus 3. If we move the a squared over to the other side, we'd have a to the minus 1. And so this must be going like a. So in a matter-dominated universe, we have delta rho over rho. These density contrasts, because of gravitational instability, are growing with the scale factor. A really simple result, independent of wavelength. And so this fact and this fact are necessary for consistency with the Poisson equation. So gravitational potentials in matter domination don't change. And one way of thinking about that is that matter is able to collapse into potential wells. Matter that it isn't experiencing any pressure support is able to collapse into potential wells just fast enough to keep the potential from decaying. So if you slow that down at all, say because you have pressure support, then the potential is going to decay. So adding radiation actually does two things. By radiation, I mean relativistic particles. And in particular, I have in mind both photons and dark things like neutrinos. First, there's the same thing I said. Pressure of this baryon photon fluid slows down the collapse. So that's just of the baryon photon fluid. But then another effect is that this density in relativistic particles is contributing to the expansion rate. Right? We have the Friedmann equation relating those two. And so we have faster expansion rate. And that means it's harder to transport matter. If delta rho over rho is going to be increasing with time, then in an expanding universe, you're kind of working against that expansion. You're trying to transport matter from an underdense region to an overdense region, and the faster you're expanding, the harder that is to do. So even the dark matter in this situation isn't collapsing rapidly enough to keep the potential constant, keep that fraction of the potential that it's sourcing constant. So both of these things mean that potential decays. And this happens just when these pressure forces start to be important. So right as you cross the horizon and these pressure forces start to be important, the potential begins to decay. And that leads to this, what I'll call a boost factor to the oscillation amplitude. Before drawing it, let me just tell you what happens. So you have the plasma compressing into potential wells, right? You have the first thing that's important, the way the initial conditions work out. Gravity is more important than pressure initially. So the initial thing is that the fluid starts flowing into overdense regions, driven by gravity. Then eventually, the pressure bounces that back, right? And this goes back and forth, and it's this acoustically oscillating standing wave. However, just as the fluid hits that maximal compression, and the pressure is about to bounce you back against the force of gravity, there's no longer any gravity operating, or the potential has nearly completely decayed. So you're maximally compressed. There's no gravity to fight against. And so the oscillation amplitude actually, if this effect is maximal, you're deep in the radiation dominant era, the amplitude boost is actually a factor of 3. And how much boost you get depends on what that fraction of matter to radiation is at horizon crossing. So this axis is rho radiation. It's the fraction of matter in radiation, relativistic particles. And we'll go to the extreme of 1, and here's 0.5. And so this is what I'm calling the boost factor for this oscillation amplitude. And if this is 1, this is 3, then, I mean, this is just highly qualitative, what I'm sketching here. But it asymptotes to this value of 3. And so this is this ratio at horizon crossing. Okay, now I had this, from what we worked out before, we should have something like this in terms of the power spectrum. This is the analog of k cubed p of k on a sphere, L squared CL. So we have something like this. And where this is 220. Matter radiate, the L that corresponds to a mode that crossed the horizon at matter radiation equality at 0.5.
Fix the mic. You lost your mic. Thank you.
That was not the right time for a mic drop. So at least in the standard cosmology, this is what we might call L eq. Right? This is so eq stands for matter radiation equality. Modes that project into wavelengths, perturbation wavelengths that project into this angular scale are the ones that cross the horizon at matter radiation equality. Yeah.
Sorry, you probably said this, but what is CL on the y-axis?
Sorry, I didn't actually say it. So all I said was that this is the analog of k cubed p of k. So this is telling us about the fluctuation power in the temperature anisotropy. That's probably more useful than telling you, I'm not sure, than telling you that, this, that it's this.
Is this like the same as that plot up there, or?
It is.
Okay.
Yeah. Yeah. Just like I said, delta rho over rho. I guess I shouldn't have squared that, but just like this is k cubed p of k over 2 pi squared. I've that plot over there, I guess I shouldn't have squared to be consistent, but that squaring should be implicit. I have delta t over t at, what was I calling this, theta lambda, right, equals, it's actually L times L plus 1, CL over 2 pi, and I just didn't bother to put in the plus 1 and the 2 pi, make that a little bit better. So this is what you usually see this plotted against, is L times L plus 1, CL over 2 pi. So L eq is about 140. So we don't, unfortunately, we don't get to see a lot of what happened. We don't get to see a large range of modes that entered during matter domination. We get to see most of what we're seeing entered during this transition, and it's a pretty slow transition, right? I mean, matter and radiation only redshift differently by 1 factor of the scale factor. So it's a pretty slow transition, and it's an important reason why the power spectrum doesn't look like this. If we take that boost factor and we square it, because we're talking about we're talking about the power spectrum that comes from 2 powers of the amplitudes of these patterns. Then we have this boost factor that goes like this and then slowly asymptotes to 9 as this multiplying thing. And so if we multiply by this, what Hu and White called the potential envelope, then that lifts all this up, and I guess we still have these big dips in this simple model, but the amplitude is dramatically boosted by this factor. A major reason we're not going to 0 here is the when the standing wave hits a null, that's when the fluid has maximal velocity, and so there's Doppler effects from the fluid that boost these up. So you don't see these coming down to 0. So so this is a huge effect in the data, right? It's in the signal that presumably is in the data of boosting this power up dramatically, and it gives us great sensitivity then to what's happening with these potentials at horizon crossing. And so it gives us great sensitivity to this ratio. And in the LambdaCDM model, we know the radiation content, right? We know the temperature of the CMB. We make these assumptions about the thermal history and neutrino production. We know the density of photons. We know the density of neutrinos. The only thing we don't know is rho matter. And it's this effect that is the dominant source of information on what the value of the density of matter is today, right? Or at any epoch, or as we often write that density today, well, in different units, so I can't say equal, omega matter, or right, which is omega matter h squared, as I was talking about yesterday. So it's a major source of information about the dark matter density, and it's in changing the history and introducing new particle content or field content that's affecting gravitational potentials. This is a hugely important constraint that makes that hard to do. You may have heard of early dark energy. This is really hard to, that's a particular model that's very tightly constrained, exactly because you have to get this effect right. Oh my God.
We're gonna have to go take our photos.
Okay, so I guess shoot. All right. So yeah. So Shirley, I'm joining you, and and I think that let me just pause by saying that so what we have so far is a temperature power spectrum that looks like this, and then asymptotes out here. That's also nothing at all like what you've seen. I don't know if you remember, but it actually looks more like this. And what drives this downward is what we'll talk about next, which is photon diffusion. And this suppression, it's very similar to if you've ever heard music from outside a car, that sound has diffused through the walls of the car, and that has suppressed the high frequencies, and so you just get this boom, 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 boom. You get the low frequencies. So the same thing's happening through the last scattering surface, suppressing. Actually, I think the physics of what's happening in the last scattering surface is a little easier than what I just used the analogy to. But OK, let's go get photographed. Thank you.